Hey everyone. We are looking at section 11.2 today, vectors in three-dimensional space. And we'll use this as an opportunity to actually learn what graphs or plotting points even in three-dimensional space looks like. So first off, we want to start by plotting two three-dimensional points. So we have 2, -1, 3, and we have 1, 0, 2. When we draw three-dimensional points, we start off with basically what looks like an XY axis, right? And then we draw another axis that is kind of slanted. The idea is that this is coming out of the page at us. Think of this like the bottom corner of two walls, right? So this is one wall, this is another wall, that's the floor, and that's the corner. So typically, we would label that as the x-axis. This is the y-axis, and this third one that goes up is our z-axis. So another way to think about it is everything that you've learned about graphing, x-y axis, is essentially the floor. Now we're moving up above or down below the floor. And when we plot these points, another thing I want to say is that there are two different ways that you could write this as well. So I've drawn the coordinate axes like this. If you also draw something that looks like this, that's also acceptable, right? The key thing is to just, when you're drawing, label your X, your Y, and your Z. And depending on where you're looking, you may even see the X and Y switched. It's kind of strange, but eh. Yeah, that's why it's important for us to label these the axes. Okay, so if I wanted to plot this three-dimensional point, I would start by going 2 along the x-axis. So here's my origin, here's the positive x-axis. 1, 2. Then I would go 1 back on the y-axis. So our y-axis is positive in this direction, negative in this direction. Right, and another thing, whenever we want something to be going into the page, typically we'll draw a dotted line, dashed line. If you ever take organic chemistry, they have a different way of drawing that, well, dashes and wedges. All right, but if I wanted to go negative on the y-axis, I would go into the page 1 unit. And then for the z-axis, 3, I would go up 3. 1, 2, 3. So if you think about it, we go x2, y -1, and then up 3. And typically there's going to be a little bit of an offset between the actual dash and the point itself, just to take depth into account. But this is what that first point would look like. The second one, we have 1, 0, -2. So I would go over 1 on the x-axis. I would not move along the y-axis at all. And then I would go down 1 on the z-axis. So x1, and there we go. And there you can see it's a little more flush with where the lines actually are, right? Because we're plotting it in a plane. It's usually the y-axis that gets wonky because of that slant. Okay, so at this point, we've drawn those 2 points. Right, we could call this point A, we could call this point B. The next part is we want to be able to find the distance between those 2 points. So I want you to think about what the line segment connecting these points would actually look like. So it's not just a straight, boom, there we go. You could draw it like that, but you have to keep in mind this is actually moving into the page, right? And if you wanted to take the organic chemistry route of noting that, you could draw some dashed lines, right? Some little notch marks to indicate that you're going into the page. Now, if I were coming out of the page, I could draw like a little wedge. So like if I wanted to draw a segment that starts at A and goes to B, I could draw a little wedge and shade that in. And that would denote that we are coming out of the page, right? And this, what I've just shown you, really isn't typical math notation. It's mainly to kind of get this idea to come across that you're either going in or coming out of the page, right? It's still a line. It's still super, super thin, right? This is just a way for us to tell what direction we're going. All right, so to find the distance between these 2 points, we can actually use something very similar to what we did in 2 dimensions. So distance is going to be the square root of, if you remember, for 2 dimensions, all we did was the change in x squared plus the change in y squared. Well, now that we have this third dimension, guess what? We just need to do the change in z squared. Yep, we're just adding another term underneath the square root. So we have change in x, we're going from 2 to 1, that's a change of 1 squared. Change in y, we're going from -1 to 0, that's a gain of 1 squared. And then for the z, we have going from 3 to -2, that's a loss of 5. So -5 squared. Remember, those parentheses are important. So when I square all of this, add it together, I get the square root of 27, which can also be written as 3 times the square root of 3, which would be a little bit more than 5, 5.1 stuff. Yeah. All right. So anyway, that's one way for us to find the distance between 2 points in 3 dimensions. This is what graphing looks like. Moving on, a little bit of an application here. Let's say we want to find the equation of a sphere that has these two three-dimensional coordinates as the endpoints of the diameter. So to write the equation of a sphere, it's basically an extension of writing the equation of a circle, right? So remember, to write the equation of a circle, you had kind of the standard form x minus h squared plus y minus k squared, leaving a space, equals r squared, right? Where r is the radius of the circle, right? This is in 2 dimensions when we have a circle. If I have a sphere in 3 dimensions, then z minus, I'll call it L squared. All right, so this is going to be the form, this basically the standard equation of a sphere with a radius of r. So to write this, I need to know a few things. One, I need to know where the center of the sphere is. Okay. The other thing is that I need to know the radius of the sphere. And I'm only given the endpoints of the diameter, which is enough for me to get everything I need. So to start off with, let's get our center. So for the center x coordinate, it's just going to be the halfway point between 5 and 0, which should be 5 plus 0 divided by 2, i.e. 5/2. The middle y coordinate is the halfway point between -2 and 4. Which is going to give us 1. And then for our z coordinate, 3 and -3, we need the halfway point between that. 3 plus -3 divided by 2, we get 0. So I can get the left-hand side of the equation from just this. We get x minus 5/2 squared plus y minus 1 squared plus z squared, right? Don't need to write the minus 0. Okay, now to find the radius, think about it. What is the radius? It's half the length of the diameter. So I can find the diameter because I know the endpoints on one of the diameters, right? So if I can find the distance between these 2 points, I have the diameter. So diameter is equal to the square root, right, of the change in x. So if I go from 5 to 0, that's a change of 5. Well, a loss of 5, but we're squaring, so it doesn't really matter. Okay, and then from -2 to 4, that's a change of 6. And then from 3 to -3 is a loss of 6. So if I add these together, we get square root of 97. And that's the diameter. So if I want the radius, I have to divide that by 2. Now, to get r squared, I'm just going to square this. So if I multiply square root of 97 times itself, I get 97. If I multiply 2 by itself, I get 4. So this would be our equation for the sphere. Little application of why this distance formula can be useful. Okay, now kind of getting back to vectors, but now extending that to 3 dimensions. First example, we want to find the component form using both of our notations. So remember we had our component form that used the little pointy brackets, and we had the linear combination of our unit vectors I and j for 2 dimensions. Thing to mention here, when we go to 3 dimensions, the unit vector for the z axis is called k. Yep, I, j, and k. So when we're doing our linear combination notation, we're going to use k to represent the z-axis. So we have our initial point, we have our final point. So to find the vector and component form, remember we do final minus initial. So the final is 0, that's the terminal, minus -2 is 2. Center point, or y-coordinate, -4, that's the final, minus 3, the initial, -7. And then for the z-coordinate, 4 is the final, 1 is the initial, that's a change of 3. So now we have our vector in component form. We could also write this in linear combination. So we have 2i minus 7j plus 3k. So here we've written our vector using both notations. The last part of this is to find a unit vector in the direction of v. So another reminder of 2-dimensional stuff. Remember, we can always make something into a unit vector if we multiply every component by 1 over the magnitude. In other words, divide every component by the magnitude. So I need to figure out what the magnitude of v is. And remember, we can basically do that using the distance formula, right, which is just an extension of the Pythagorean theorem. But since we already got our vector in component form, we don't have to go through the mental labor of figuring out what the change is in each coordinate. We could just take these components and go with it. So magnitude, we'll get 2 squared plus -7 squared plus 3 squared. So that's going to be 9 plus 4 is 13. Add 49 and you get 62. So the magnitude of that vector is the square root of 62. So my unit vector is going to be my vector v divided by the magnitude. So and I can use either notation here. For the unit vector, it didn't really say I had to use one or the other. So I'm going with the pointy brackets. My x component is going to be 2 divided by that magnitude. Y component, we've got -7 divided by the magnitude. And z component, we have 3 divided by the magnitude. And if you really, really wanted to, you could square each of these components, add them together, square root the total, and that should be 1 if this is a unit vector. All right. So this would be our answer for that one. Okay. So next thing, remember that two vectors are equivalent if they have the same magnitude and direction. Right, if they have the same magnitude, same direction. And one way that we explain this with two-dimensional vectors is basically if I have two vectors that look like, say, this and this, right? If they're going the exact same direction, meaning the angle with the horizontal is the same for both of them, and they're the same length, then what would happen is if I were to translate, meaning just move, shift, each of these endpoints so that the initial point's at the origin, they would end up looking exactly the same. So one vector would be here with that same angle. The other vector would be literally right on top of it. It'd be like if I were to draw the exact same thing, that's the second vector. All right, so remember that's what equivalence meant for us in two dimensions. All right, let's look at these. Let's look at these two vectors and kind of determine if they're equivalent. So for the first vector, we have 2, 1. So we've got the initial point at the origin, terminal point right there. And that's that first vector. Second vector, we'll start off at the origin as well, but this time we'll go back 2 and down 1. Hmm. Strange. So they don't exactly overlap like this one does. Because of that, we cannot say that the two vectors are equivalent. But there is something special about this particular set of variables. And you can think of it in, well, two different ways. One is that these two vectors, like if you think about it, this angle and this angle are going to be exactly the same. In other words, these vectors, when put together like this, form a straight line. It's one way to think about it. Another way to think about it is if I were to shift either of these vectors, like move, translate, shift anywhere, the lines that would be formed by these vectors would always be parallel to each other, right? Think if I were to take this vector and scoot it up like 3 units, it would be right here. If I were to extend that into a line, it would be parallel to that vector. So we can say, in this case, collinear, putting in quotes, and parallel. So in this case, we would say that the two vectors are parallel, right? Parallel refers to vectors. The points that form these two vectors, we would say are collinear, right? Because the points are on the same line. So the terminal points and the initial point are collinear. So we use this word for points, we use this word for vectors. And I do want you to think about something here. What's the difference between these two component forms? Right? You might say, okay, both of these are negative, right? It's basically like if I were to take this vector and multiply each component by -1. In fact, what we'll find is that if I were to take one vector and multiply every component by the same number, the result would be a parallel vector. It may or may not be equivalent, but it will be parallel and the points will be collinear. So two vectors are parallel. If two vectors are parallel, then they are scalar multiples. Right? Meaning what I just said about multiplying each component by the same number, right? Since we're multiplying by a number, that's where the scalar part comes in. So for the next example, we have a vector called W. It has this initial point, it has this terminal point. We want to determine if each of these vectors given is parallel to W. So the first thing we would need to do is figure out W's component form. So off to the side, I'm going to write W out in component form. So remember, final minus initial. Okay, so for X, -4 minus 2. For Y, 7 minus -1. And for Z, 5 minus 3. Okay. So we have the component form for W. Basically, if we can say that each of these is W times a number, then then that vector will be parallel to W. So for this one, is there a number I can multiply W by or divide W by? Because remember, division is multiplying by 1 over. All right, so is there a number I can multiply all the components of W by that will give me U? Yes. If I were to divide each of these components by -2, I would end up getting all of the components of U. So we would say that U is equal to -1/2, since we divided by -2, times vector W. Since U is a scalar multiple of W, the answer to this one would be yes, U is parallel to W. And remember, those two lines mean parallel. Okay, now let's look at V. So is there a number that I can multiply each of these components in W by to get the components of V? Well, at first glance, you might say, why don't we try -2? Because -6 times -2 gives me +12. 8 times -2 gives me -16. But 2 times -2 gives me -4. Didn't quite work out. And the thing is, there's not if it worked for two, if that number worked for two of the components and not the other, there's not going to be a single number that I can multiply everything by to get this. So for this one, we would say no, V is not parallel, right? Parallel with a slash through it to W. Since there's not a number or a scalar that we can multiply W by to get V. Moving on to the next example, determine whether the points blah, blah, and blah are collinear. So essentially, if we're basically going to look at two different vectors, okay? If those two vectors turn out to be parallel, remember that means that we can always shift them to, yeah, backtrack. Let's think of it this way. PQ, right? We can use P as the initial point. We can use Q as the final point. So PQ, we're going to get 2 minus 1, 1, 1 minus negative 2, and 0 minus 3. So that's PQ. If I were to go to PR, and here the reason I'm doing PR instead of QR is I want to have the same initial point, right? Here's the idea. I've basically figured out that PQ is this guy, not drawn to scale. Actually, let me try and make it a little more accurate. So basically we figured out that PQ is this guy, right, coming out of the page. So we could draw a little wedge there if we wanted to, right? So the idea is if I look at PR, this is point P, we can figure out if we're going to end up getting the same kind of thing that we had on the other side of the paper with the two-dimensional vectors, right? And if that's the case, then we get collinear points. So looking at PR, again, P is your initial, R is your final. So 4 minus 1, 7 minus negative 2, and negative 6 minus 3. Okay, what do you notice about PQ and PR? You should notice that 3 times PQ is equal to PR. Which means that those are parallel vectors. And in component form, remember, we've actually shifted the vectors so that their initial point is at the origin. Right? If I were to look at that, PQ would be this guy. PR would basically be if I were to triple the length of PQ. So that's a continuation of that wedge. So if you think about it, we have P here, we have Q here, we have R here. They're all on the same line because these two vectors are parallel. So the idea, we pick an initial point and we use the other 2 points as terminal points. We figure out the vector and component form for each possible combination there. All right, so PQ and PR. And we look to see if those vectors are parallel to each other. If they are, then your points are collinear. If they are not, then your points are not collinear. Right? So that's a nice, oh yeah, answer the question. So the answer to the question is yes. Okay. Looking at the next one, write the vector v equals 4i minus 5k in component form using the pointy brackets. So main thing here is I want you to realize that they skipped j. When that happens, that just means that the y component is 0. So that would be 4, 0, -5. Next example, find the terminal point of vector v given that the initial point is -2, 3, 5. So remember how each of these components work. We get them from doing final minus initial. So the final x minus the initial x, so minus -2, is equal to 7. Okay, so what plus 2 is 7? That would be 5. For the second one, we have the final y minus the initial y is equal to -1. This would mean that y has to be equal to 2. And then for our z, we've got final z minus the initial z, which was 5. And that's going to be equal to the z component of the vector, 3. All right. And what number minus 5 gives me 3? That would be 8. So the terminal point would be the coordinate 5, 2, 8. Two more examples. First one, find the magnitude of the vector v. Okay, then find a unit vector in the direction of v. So same thing that we looked at earlier, right? The magnitude we can get from our distance formula. Since we already know each component, we can use those as the change in x, y, and z. So we have the magnitude, which I should have labeled, right, is equal to -6 squared plus 2 squared plus -3 squared. So adding those, we get 36 plus 13, also known as 49. Square root of 49 is 7. So then unit vector, remember, is going to be our vector v divided by the magnitude. So if I were to write this also in linear combination form, we would have -6 over 7i plus 2 over 7j minus 3 over 7k. And that's our unit vector. That's our magnitude. And now we have one more question that is kind of an application question. So we have a television camera that weighs 120 pounds. It's supported by a tripod, and it meets the floor at these 3 coordinates. Write the force exerted on each leg of the tripod as a vector. Okay. So with these kinds of questions, I like to make everything a picture first. So if I have a video camera here, we'll say that's a very old school video camera. Yep. From the 1900s. Okay, so we've got our video camera and we've got our tripod. All right, and we have coordinates for each of these tripods. Essentially, we want to figure out the force exerted on each of these legs. Okay. So the height is also going to be something important to know here. We're going to call that the height h, right? Then we know the coordinates for each of these points. So force, okay. Force, because remember in the last video I mentioned that one of the most important things you can do is read a question and figure out whether your answer is supposed to be a vector or a scalar. Force generally is a vector. The magnitude of that force would be a scalar, right? And if you have a force being applied in one dimension, then that's all there is. But we live in a three-dimensional world, and that's pretty rare. So we're basically writing a three-dimensional vector for each of these legs. Thing for us to note, though, a couple things to note actually. Because these are evenly spread out, as is typical with tripods, we know that the force on each leg is going to be equivalent to the force on any of the other legs. So realistically, I only need to know, yeah. So realistically, I only need to know basically one of these vectors. If I know one of them, then I can get what I need for any given leg. The other thing is how the weight of this comes into play. So common thing with these kinds of force physicsy questions is the idea of gravity. So the force being applied is also going to kind of be at the mercy of this 120-pound weight. So we're going to start off by just getting vectors that go from this point to each of these points. So to do that, we would pick our favorite vector. Why don't we just do it for each of them? We'll call this leg number 1, number 2, and number 3. Okay. Actually, I don't even need those labels. Let's just use PQR. So for P, okay, our initial point is going to be the coordinate of this camera. So I already know the z coordinate is the height, right? And yeah. So we know the z coordinate's the height. For the x and the y coordinate, though, we're going to assume that this is exactly in the middle of those 3 points. And one thing you might have noticed about those 3 points is that they are essentially unit circle coordinates. And the center of the unit circle is the origin. So we know that the initial point is going to be 0, 0, h. The final point is going to be each of P, Q, and R. So, yeah. So for P, initial or final minus initial, 0 minus 0 gives me 0. -1 minus 0 gives me -1. And 0 minus h gives me -h. If I wanted the force exerted on vector P on this leg P, I would have to multiply that by the weight, the magnitude of this force. And that would be the force for vector P. Now, since this question specifically says each leg, I should probably do it for Q and for R as well. So for Q, switch to my pen, sharpen that. So for Q, final minus initial, square root of 3 over 2 minus 0. Final minus initial, 1/2 minus 0, and 0 minus h. Right, that's the vector that goes from the camera down to the floor. Now, if I multiply that by the weight or the magnitude of the force, right, then we end up getting the force put onto leg Q. If I multiply 120 times the square root of 3 over 2, I'm going to pay attention to that over 2 first. 120 divided by 2 gives me 60. So that would be 60 over 3. Y component will get 60. And the z component, we still have negative 120 times the height. And that's the force exerted on leg Q. And lastly, we have R. And in a similar fashion, we'll end up getting, oh, whoops, getting ahead of myself there. Negative square root of 3 over 2, positive 1/2, and negative h, right? Just final minus initial, final, initial. If I multiply that by the magnitude of the force, I get negative 60 root 3 as the x component, 60 is the y component, and negative 120h as the z component. And that is the force exerted on leg R. So forces are vectors, right? Weight typically represents the magnitude of a force. And if we have sort of a position vector like we did here with the camera as the initial and the floor point as the final, then we can multiply by the magnitude to get the force as a vector. Pretty fun stuff. And it's one of the reasons why this course actually makes physics make way more sense. You'll appreciate that a lot more by the end of the last part of the course. But yeah, so three-dimensional space, I've learned how to kind of work through that, how a lot of the extensions come into it from two-dimensional space, right? And then we did a little fun problem about force. And that's all I've got for this lesson. You can now go through and do that second assignment. Happy mathing.